Okay, so this lesson is on lines in 3-space. We're learning to find vector, parametric, and symmetric when possible of a line in 3-space. And we're learning to find the shortest distance from a point to a line in 3-space as well. And the great thing about 3-space is we can just extend what we know about 2 dimensions to 3 dimensions. So this would be our origin, 0, 0, 0. This is a point we know on the line, and it would have like coordinates A1, A2, A3, X, Y, and Z. And then this is some point we don't know. And again, we can say that R would be the vector from OA plus R is this here, this is R, is going to be OA plus AP. And here's vector AP, which is going to be, we can use small letter a, plus a scalar multiple of the direction vector of this line. So M is the direction vector of this line here. Okay? So vector, parametric, and symmetric equations of a line that pass through the point A, A1, A2, A3 with direction vector M equals M1, M2, M3 are just like we would expect them to be, noting in the symmetric equations that none of the direction vectors can be 0. I'll show you what happens if that happens to be the case. So our first question, a line passes through the points A, -2, 5, 3, and B, 2, 4, 1. Find the vector, parametric, and symmetric equations of the line. Okay. So the first thing we're going to do is find the vector from A to B. And that would be B minus A. So we would get 4, -1, -2. And see if we can take a smaller scalar multiple, and we can't. So that's going to be our direction vector. 4, -1, -2. So our vector equation is going to be R equals, so we could choose either point A or point B. I'm going to choose point A, -2, 5, 3. So this represents the vector from 0, 0, 0 to -2, 5, 3, plus the parameter t times the direction vector for -1, -2. So there's the vector equation of the line in 3-space. Then we can get the parametric equations. So the parametrics can be found, they're going to be x. The x coordinate can be found by doing -2 plus 4 times t. The y, 5 plus t times -1, so that's 5 minus t. And z is 3 subtract 2t. And then to get the symmetric equations, remember you mentally solve for t in each of these. So here, if I solve for t, it would be x plus 2 over 4 equals y minus 5, if I got t by itself here, divided by -1 equals z minus 3 over -2. So there's our symmetric equation. Okay, so determine the vector and parametric equations of the line that passes through the point 2, 7, -3 that is perpendicular to the xz plane. So here's where I'm going to start talking about the 3 planes and show you a model that I've made. So to do that, I have to change my camera here and change my lens. Sorry about this, but let's see it up and down. Okay, so here's a model I've made, and really what we want to talk about is what is the xz plane and how can we be perpendicular to it. But before we do that, I want us to start getting familiar. So here's my setup here. So this red pen represents my x-axis. Okay, so x-axis is going to be coming right at you, like straight forward at you, out, and then in is going to be the negative x-axis. And the y-axis here, positive y-axis is to the right. And then if I was continuing, the negative x-axis would be to the left over there. Okay, so positive to the right, negative to the left. And the z-axis, the positive z-axis is up, and then the negative z-axis would be down. So this point in here where the x-axis, y-axis, and z-axis intersect is the point 0, 0, 0. So we're getting good with axes. Planes are where the different axes intersect. So we, for years, were dealing with the xy plane always. And in grade 9, we had the y-axis was up and down, and the x-axis was left and right. And this is a representation of the xy plane. We know it extends infinitely in both directions. It's flat, okay? And it can be represented part of it by this rectangle. But then what happens once we add the z plane is the xy plane turns on its side like this. This becomes our y-axis, left to right. Our x-axis goes forward and backwards, and then we add this new dimension, the z-axis, which is up and down. And that's the model that I've made for us here. So this is my x-axis and my y-axis, and they form this xy plane here. Okay, so the xy plane is this flat plane here. This is my xy plane, where the x-axis and y-axis intersect. So any points along here would be considered to be on the xy plane. Okay? And if a point were to be on here, its z value would have to be 0 if it were on the xy plane, which makes sense. Where the y-axis and z-axis meet, we have the yz plane. Okay? But our question asks about the xz plane, so that's where our x-axis and z-axis meet. So here I've got our xz plane. So here's our x-axis and our z-axis, and where they meet, we've got this xz plane here. Now the question says determine the vector and parametric equations of the line passing through the point 2, 7, negative 3, perpendicular to the xz plane. So perpendicular to the xz plane. So say I want a direction perpendicular to this plane. Here's this plane, here's perpendicular. Well, perpendicular to the xz plane happens to be in the y direction. Okay, perpendicular happens to be in the either positive or negative y direction, or parallel to the y-axis. So that's what we want to get out of here, is if we want a direction perpendicular to the xz plane, it's going to be parallel to the y-axis. Okay, so I'm going to turn my camera back over and switch my lens around so this is right side up again. So we looked at that model so that we kind of had an idea of what it was they were talking about with the xz plane, but also that being perpendicular to the xz plane meant we were parallel, or in the direction of maybe perpendicular to the xz plane is in the direction of the y-axis. So if we want to make a direction vector that's parallel to the y-axis, the easiest one for us to make would be 0, 1, 0 as my direction vector. Okay, so 0 in the x direction, 1 in the y direction, 0 in the z direction. That gives me a direction parallel to the y-axis. So if I want a vector equation, my vector equation of the line that goes through this point with this direction is going to be r equals 2, 7, negative 3, plus my parameter t times my direction vector 0, 1, 0. And then we also want the parametrics here. So x is going to be 2 plus 0t. I don't need to show that, so x is going to be constant. Y is going to be 7 plus 1 times t, so 7 plus t. And z is always going to be negative 3. All right, so we found the vector and parametric equations of the line passing through that point perpendicular to the xz plane. And we figured out using models that perpendicular to the xz plane was parallel to the y-axis. Question 3. Does the point -3, -8, -13 lie on the line passing through this point, A101, parallel to this line? And parallel means same direction as. In other words, it would have the same direction vector as this line. So the line that we're talking about then would be the line passing through that point with the same direction vector as this line. And we want to see if this point is on this line or not. And when we're testing whether a point's on a line, we use parametric equations. So I'm going to spread my parametric equations of this line out. So I've got x equals 1 plus t, y equals 0 plus 2t, and z equals 1 plus 3t. And I'm testing the point -3 for x, -8 for y, -13 for z. And again, I'm going to see, do I get the same t value in all three cases? If I do, then yes, the point's on the line. If I do not, then it is not on the line. So solving for t here, I would subtract 1 on both sides, and I get t is -4. Here I would divide both sides by 2 to get t, and I still get -4, so I'm hopeful. In this case, I'm going to subtract 1 on both sides, and then divide both sides by 3, but this one I do not get -4. So therefore, the point -3, -8, -13 is not on the line. Question 4, find vector, parametric, and then symmetric with a little star here. So what does that asterisk mean? Equations of the line passing through the points P and Q. So first I'm going to find the direction from points P to Q. So Q minus P is going to give me 3, 0, -6. And so I would choose my direction vector to be, I could divide each component by 3 to get a smaller scalar multiple. So my vector equation is going to be r equals, I'll choose point P, 2, -2, -8, plus the parameter times the direction vector. Here's my vector equation. My parametric equations. So x value is going to be 2 plus t, y value -2 plus 0t, so just -2, and z is -8 minus 2t. Now symmetric equations. So notice that we have a direction number, our second direction number being 0 here. So, and you can see here there's no t. I can't get t by itself in my y parametric because there is no t. So how do you write the symmetric equation when one of your direction numbers is 0? It's still possible, but it looks different. So what I'm going to do is solve for t in my x parametric. So that's going to give me x minus 2 over 1. And in my z parametric, I solve for t in my z parametric, I would get z plus 8 over -2. And because I can't solve for t and y, I use a semicolon and then say y is always -2. Y is a constant. It doesn't depend on t. So that's how you show the symmetric equation of a line in 3 space that has one direction number 0. And you have to be thoughtful then, if you're given the symmetric equation and you want parametrics or vector, you have to be careful because it's common for people to think that, for instance, the point would be 2, -8, -2 because these two come first, but really the point would be opposite of this 2, same as this because y is a constant, -2, 2, -2, -8, which is in fact what the point is, 2, -2, -8. And again, the direction vector, if there is no, if it's after the semicolon here, we don't have a denominator, the denominator is 0, so our direction vector is 1, 0 for the y direction number, and -2 for the z direction number. Something to watch out for, and we'll have examples where that happens. So question 5, the symmetric equations of a line are given as x minus 3 over 2 equals y plus 4 over -3 equals 1 minus z. And it wants us to write vector and parametric equations of the line. So the first thing you always do is you ask yourself whether this really is in symmetric form or not. Okay? And to be in symmetric form, x, y, and z have to be first. So the x is fine, the y is fine, but here we've got 1 minus z instead of z first. Okay, so what we do then, if we want to rewrite this with z first, it would be z minus 1 over -1. And again, our reasoning is if we have 1 minus z and we multiply by -1 over -1, we're going to get -1 times 1 minus z over -1. So we're just multiplying by 1. Distribute. Write the positive z first and the -1 second so that it's in symmetric form. And then we're transferring that up to our equation. Okay, so now we have it in symmetric form, and that's important because we want to know the point. And for our vector equation, we want to know the point and the direction. So the point is going to be 3, -4, +1, plus t times, so our point comes from the opposite, it's from here, and the same direction numbers from the denominator. So plus t times our direction vector, which is 2, -3, -1. So that's our vector. And our parametrics then are going to be x equals 3 plus 2t, y equals -4 minus 3t, and z equals 1 minus t. Determine the coordinates of another point on the line. So we can let t equal anything we want. So I could let t equal 1, for instance. If I want to use my parametrics, x would equal 3 plus 2 times 1, which is 5. Y would equal -4 minus 3 times 1, which is -7. And z would be 1 minus 1, which is 0. So that would mean that 5, -7, 0 is another point on the line. Okay, number 6, write a vector equation of each line. So in 6a, first thing we would do when we're given symmetric equation is make sure it truly is in symmetric form. So I can see the x part's fine, but here we have to change 3 minus y to y minus 3, which means we have to multiply the bottom by -1 as well, making it -2. So our vector equation, our point's going to be 4, 3, -2, plus parameter t times our direction vector, which is 2, -2, 5. So there's a vector equation of the line in A. The line in B, again, we're given symmetric equations, and we want to make them look like symmetric equations. So here we've got -x, but we could rewrite that as x over -1. And we can rewrite y plus 2 as y plus 2 over +1. And we can rewrite z minus 3 as z minus 3 over +1. So now the direction vector pops out at us, or the direction numbers pop out at us. So the vector equation is going to be r equals 0 as part of our point, -2, 3, plus a parameter t times the direction vector, -1, 1, 1. Next question, again, we're given symmetric form. Okay, so this is an example where one of our direction numbers was 0. So be careful here where we're finding our point. It's going to be 5, then y is always equal to 8, 5, 8, negative 2, plus t times our direction vector, which is going to be 3, 0 for y, because y is after the semicolon over here, and not part of the symmetric part here. 3, 0, negative 4. D, we want the vector equation of the point through this, sorry, of the vector equation of the line through this point parallel to this line. So parallel means same direction vector as. So the vector equation is going to be r equals 4, negative 1, 0, because it goes through this point, plus t times the direction vector of this line, because we're parallel to it, which is 3, negative 1, 1. The coefficients of t form the direction vector. And E, the line passing through that point, perpendicular to both of these lines. Perpendicular to both lines. So how do we find a direction perpendicular to two directions? Well, we know that that's the cross product. That's the definition of the cross product. So if we have two different directions and we want a direction perpendicular to those two different directions, we cross them and we get a direction perpendicular to both of them. Okay, so if we want a direction perpendicular to both of these lines, we would want the direction vector of each line. So the direction vector of this line, make sure it's in symmetric form. X, Y, and Z are each first here. So the direction vector is 3, negative 2, 5. The direction vector of the second line, also in correct symmetric form, is 6, negative 4, 3. And we want to find their cross product because that's going to be the direction we want to be in. So we'll do our little 3, negative 2, 5, 3. Start here. So it's going to be negative 6 subtract negative 20. 30 subtract 9. Negative 12 subtract negative 12. So M1 cross M2 is going to be 14. 30 minus 9 is 21. Negative 12 plus 12 is 0. And we can choose for our direction. We can call it M3 or just plain M. I'm going to take a smaller scalar multiple and divide each of those by 7, which will give me 2, 3, 0. So there's my direction perpendicular to both of these directions. So the vector equation of my line contains this point plus parameter t times my direction vector 2, 3, 0. So there's the equation of a line going through this point perpendicular to both of those lines. Question 7, classify each pair of lines as coincident, parallel and distinct. So coincident, again, the same line. Parallel and distinct. So two lines that are parallel never touch. Perpendicular, so 90 degrees to each other, or none of the above. So the first thing we're going to do is get the direction of each line, and then we'll be able to say whether we have one of these two possibilities, that the lines are exactly the same line or they're parallel and distinct. So in this case, the direction vector of the first line is 1, 2, negative 3. This one, though, I have to rewrite. So in the first case, I'm going to change 1 minus x over 2 to x minus 1 over negative 2. 5 minus y over 4 to y minus 5 over negative 4. And z over 6. So now I know that my second direction is negative 2, negative 4, positive 6. Okay, and now I'm going to look at those two directions and see if they're scalar multiples of each other. And it looks like if I multiply m1 vector by negative 2, I get m2 vector. So that means m2 vector is negative 2 multiplied by m1 vector. So if I multiply each of these components by -2, I get this vector here. So this means that the lines are either parallel and distinct, so we either have coincident lines, they're the same, or we have parallel and distinct lines. Those are our two possibilities. And our test to see which one of those two we have is to see if a point we know is on one line is also on the other line. So what point do I know on this line? Well, I know that the point 1, 5, 0 is on this line. If it's also on my first line, then I know that the lines are coincident. So my test is going to be, is the point 1, 5, 0 on R1? And I'm going to convert this into vector form and then parametrics. So vector form here would be 2, -3, 4 plus t 1, 2, -3. And my parametrics, I'm going to split them out. So x equals 2 plus t, y equals -3 plus 2t, and z equals 4 minus 3t. And I'm testing to see if this point that's on my second line is also on my first line. So I'm going to put 1 in for x, 5 in for y, and 0 in for z, and see if I get the same t in each case. So here if I subtract 2 on both sides, I get t is -1. Here I would add 3 to both sides. Divide both sides by 2, and I get t is 4. So right away I don't get the same t. I wouldn't here either. I would get t is 4/3. Okay, so since this point is not also on this line, then the two lines are not coincident, they're parallel and distinct. So since P150 is not on R1, the lines R1 and R2 are parallel, they have the same direction, but they don't have any points in common, and distinct. Okay, so we've got another pair of lines here. First one's given to us in vector form, so it's easy to tell that the direction vector of the first line is 5, -2, 1. And this is in symmetric form, so M2 is going to be 6, 11, -8. And quickly by looking, you can see that they're not scalar multiples. And a way you can say that is M2 does not equal KM1, not a scalar multiple. So therefore we know that they're not coincident, or parallel and distinct. Those two are off the table. And our only two other choices for now are either they're perpendicular, so they could be in perpendicular directions in a lot of different ways in 3 space. But we can figure out if they're perpendicular to each other by doing the dot product of the directions. If the dot product of the directions happens to be 0, then the lines are perpendicular, or we can choose none of the above. So now we're going to test to see if they're perpendicular. So we're going to test and see what M1 dotted with M2 is. And we know if their dot products ends up being 0, then they are perpendicular to each other. So 30, dot product is multiply and add, so 30 minus 22 minus 8 is 0. Okay, so since the dot product of their directions is 0, therefore R1 is perpendicular to R2. So it's different implications as it would have in two space. In two space, if they're perpendicular, they're gonna meet somewhere, but in three space, not necessarily. They could meet, okay, on an angle somehow, or they could not meet and still be perpendicular, okay? And we'll talk about that later. But we know that their directions are perpendicular anyways. All right, so we're gonna move on to deriving the formula for the shortest distance from a point to a line in three space. So different than in two space. So here's our line that we're talking about right here. R, okay, there's our line. It's got a known point Q. So Q is a point we know on the line. And we're trying to find the shortest distance between this line R and this point P, okay? So I'm going to draw in the vector QP. So here's our vector QP. And the shortest distance from a point to a line in three space is going to be perpendicular to the line. So this distance here, which I could say is the magnitude of vector dp, for instance, is going to be our shortest distance. Okay? And I'm going to say that we form a right triangle here, and this is going to be my angle theta right in there. So if I have a right triangle, then according to angle theta, this shortest distance here I want is the opposite side, according to trigonometry. Across from the right angle is my hypotenuse. And then from Q to D here would be my adjacent side. So it's fair to say that the sine of angle theta is going to be the opposite over the hypotenuse, or the sine of angle theta is the magnitude of vector dp over the magnitude of vector qp. And vector dp again is the magnitude of vector dp is going to be that shortest distance that I want. So if I multiply both sides by the magnitude of vector qp, I'm going to get that the magnitude of vector dp is going to be the magnitude of vector qp times the sine of theta. And again, q is a known point on the line, and p is a point I'm trying to find the distance to. So I would know both of these points. Okay, I know this point, q, and I know this point, p. Okay, so keep that in mind. So the magnitude of vector dp is the distance I want to find, the distance, the shortest distance from the point to the line in three space. Now, we know that the magnitude of the cross product of two vectors, so for instance, I'm just going to get a piece of paper here. If we want the magnitude of vector A cross B, we know that that's the magnitude of vector A times the magnitude of vector B times the sine of the angle between them when they're tail to tail. And that's so, say I have a vector A and a vector B meeting tail to tail with an angle theta between them. The magnitude of their cross product is the magnitude of vector A times the magnitude of vector B times the sine of theta. We know that gives us a vector perpendicular to both of them. That's our geometric definition. So I notice here that if I multiply by 1 in, so here's theta, and so here's QP. Now this direction here, so here's the direction of QP, and then this is the direction of the line. So this line has direction M, and then between, theta is between the direction of QP and the direction of the line. So QP sine theta times the magnitude of M is the magnitude of the cross product between these two vectors when they're tail to tail. But if I multiply by M, the magnitude of vector M, I also have to divide by the magnitude of vector M. So really I'm just multiplying by 1 in a great way. So I'm multiplying by 1 by multiplying the top by the magnitude of vector M and the bottom by the magnitude of vector M. But then it just so happens that the top ends up being the magnitude of the cross product of QP and the direction vector of the line. So the formula for the distance, the shortest distance from a point to a line in 3 space is the magnitude of QP, the cross product of QP and the direction vector of the line, divided by the magnitude of the direction vector of the line. So again, Q is a point we know on the line, P is our point we want the shortest distance from, and M is the direction vector of the line. And theta is the angle between QP and the line, but theta gets absorbed because it ends up being the magnitude of the cross product. So here's our formula to get the shortest distance from a point to a line in 3 space. And we're going to use that formula now to find the shortest distance from the point P212 to the line R equals 131 plus T times 322. So again, let's write our formula down. And then, so Q is a point we know that's on the line. So Q is 131, P is 212, and M is the direction vector of the line. So we know all 3 things we need here. QP, so it's going to be 2 minus 1 is 1. 1 minus 3 is -2, 2 minus 1 is 1, crossed with our direction, 3, 2, 2, magnitude of that over the magnitude of the direction vector. So it's going to be 9 and 4 is 13 and 4 more is 17. Then I'm going to do my cross product. So it's going to be -4 minus 2, 3 minus 2, 2 subtract -6. Magnitude of the vector, so -6, 1, 8. The magnitude of a vector, so square root of, it's going to be -6 squared is 36, plus 1, plus 64. So the root of 101 over the root of 17, which is also the root of 101 divided by 17. Which is approximately 2.4 units. Shortest distance from this point to this line. Okay, number 9, find the distance from that point R to this line. Okay, so first of all, we're going to exaggerate this line so we can tell its point and direction vector. So we know a point on the line Q is going to be 0, 0, 1. And we know the direction of the line is 1, 2, 1. And this is our point R. Okay, we can use it R instead of P if we want to. So we can modify our formula if we want to, or we can change that point to point P if we want to. So I'm going to say, instead of QP, I'm going to say QR crossed with the direction vector of the line divided by the magnitude. So QR is going to be R minus Q, so 0 minus 0, 1 minus 0, 5 minus 1, crossed with our direction vector over the magnitude of the direction vector, which is square root of 1 squared plus 2 squared plus 1 squared. Now I'm going to do my cross product. So that's going to give me the components 1 minus 8, 4 minus 0, 0 minus 1 over the square root of 6. So it's going to give me -7, 4, -1 vector, magnitude of that vector over the square root of 6. So that's going to give me the square root of 49 plus 16 plus 1, which is 66, over the square root of 6, which is the square root of 66 over 6, which is the square root of 11, or approximately 3.3 units. So the shortest distance from the point R to this line would be approximately 3.3 units. So our success criteria are that we can find vector, parametric, and symmetric equations of a line in 3 space. Remember to be careful about when symmetric equations are given. Is it actually in symmetric form? Are x, y, and z first? Is there a semicolon? Is it for x, y, or z? Be careful with that. I understand with all my heart that lines in 3 space do not have a unique normal, and therefore they do not have a scalar equation. We'll talk about that more. But they do only have vector, parametric, and symmetric equations. A line in 3 space does not have a unique normal. So here's a line in 3 space. There's an infinite number of ways you can be perpendicular to this line, so it doesn't have a normal. Okay, so that means it doesn't have a scalar equation. And we can find the shortest distance from a point to a line by using this formula, which is D is the magnitude of QP cross M over the magnitude of M. All right.